Hello and welcome to ICDD's InSession webinars. Soon you will hear ICDD's Executive Director Tom Blanton presenting the webinar Navigating a Powder Diffraction File entry. Please remember to visit icdd.com for information on future free webinars, educational events, product information, and to purchase ICDD's databases and software.
So let's begin with talking about powder diffraction, and typically the principal application or the major application is in fact phase identification. We start with some type of sample. We go through a number of steps for the sample preparation. The sample is placed in a diffractometer and we collect a data set. And the typical data set is a plot of the intensity versus the diffraction angle to theta. And from that, we then compare typically in diffractometer vendor software, the peaks that we observed in our data with some list of despacings, intensities, and chemistry. And from that, we try to come up with a phase identification result. And what we're going to talk about here today is the powder diffraction entries, or cards, that sometimes people refer to them as, with the idea that there is a lot more information in the PDF entries beyond despacings, intensities, and chemistry. So the start of the powder diffraction file, or the origins, began in 1938 with a paper published by Hanawalt, Wren, and Fravel from the Dow Chemical Company. And what this group did was they showed that powder diffraction could be used for chemical analysis of materials. Now, people have been analyzing powder diffraction for several years. They had shown that different materials had different diffraction patterns, but Hanawalt came up with a method, today referred to as the Hanawalt method, that used the XRD data for the phase ID application. In 1941, the first powder diffraction file cards were published. This is through ASTM. There were 978 entries. They actually put the data on a index size card. They were handwritten entries, and they were a publication that included despacing, intensities, and a little bit of chemical information, and information about what were the three most intense diffraction peaks to help with the phase ID. Now, the reason the original entries were in despacing is because different people might be using different radiation wavelengths, and so the dspace was the constant based on the unit cell or the structure of the material. Today, the powder diffraction file, 2021 databases, comprised of PDF4 plus, 444,000 plus entries, of which 336,000 plus have atomic coordinates. So you use this for phase ID as well as quantitative analysis. The minerals database, which is a subset of PDF4 plus. We have the organics database, which emphasizes organic materials, particularly useful for people studying pharmaceuticals, pigments, dyes, etc. The PDF2 database, 316,000 entries, is used primarily for phase ID. You can do semi-quant with the I over IC values for RIR method. So a combination of the different databases, one can select what's the best one for your particular applications. In addition, we have our Jade software, when combined with the database, makes a very powerful tool for phase ID, quantitative analysis, and materials characterization. The PDF4 plus database, which will be the emphasis of today's presentation, is comprised of data from ICDD, both experimental and crystal structure data, including data from our grant and aid program. We have the Phys ICSD data in the PDF4 plus database. We have a selection of NIST data, and we have data from the Linus Pauling file, all of which comprises to make the PDF4 plus product. Want to talk about this past year, 2020. We renewed our partnership with CCDC, and in our PDF4 organics database, we are including CSD data for phase ID and quantitative analysis purposes. So the organics is a large amount CSD data, again, a selection of NIST data, and we have both Phys and ICDD data. So when you're studying, for example, pharmaceuticals, and these pharmaceuticals are the full pill, the full capsule, with both the API and excipient, it's the complete package that allows you to do full analysis of these materials. So when you start with your PDF4 Plus database, you have an icon on your desktop. You open up that icon, and what you will first see is what we would refer to as a data mining menu. Now today, we won't be talking extensively about data mining. That will be a future webinar coming up in March. But I want to point out some of the things you should be aware of that are related to the PDF4 database. And in particular, there are a number of search capabilities. I want to mention that we do have subfiles. So if you're working on a particular type of material, you can select that subfile to simplify your phase identification applications. In addition, I mentioned that we have the different databases that comprise PDF4 Plus. So we have our ICDD data, ICSD, Phys data, NIST, LPF, and our own crystal data. CSD is grayed out here because that you will find in our organics product. The other thing I want to talk about are quality marks. All ICDD entries, whether you refer to it as an entry or a card, go through an editorial review process. This is unique to the ICDD database. And what that means is that we look at the data, because some of it was generated by ICDD, but a lot of the data is extracted from the literature. We review that data for the quality, and we give quality marks where we have the highest quality, mid quality, and then low quality data. Sometimes we get asked, well, why would you have low quality data in the database? And the reason is that sometimes that's the only data that's been published in the literature. So we want that information available to you, the user, but we also want to call attention to the fact that we've reviewed the data and there are some issues with the data. We make a note what the issue is, so you can at least compare your data to the PDF entry and understand the limitations of what was in the literature. Another thing that is unique to the powder diffraction file is that our quality management system is ISO certified. Again, something that's unique to the PDF databases that you won't find in any other crystallographic databases. So if you're working with data that's going to be reviewed by regulatory agencies, and they ask questions such as, how do you know your instrumentation is good? How do you know that your data are good? How do you know your database is good? You can say that the ICDD databases carry ISO certification in the quality management system. So let's say you want to open a specific PDF entry, and specifically you know the PDF entry or card number of interest. So an example here is 0006300315. 00 tells you it's from the ICDD data, that's 00. 063 tells you the set number, and 0315 is the entry or card number. So you would enter that information, and then you can open up the PDF card. So here's an example. We entered the number, we opened up the PDF card, and now here is your PDF card or PDF entry. It's for a bismuth iron scandium alloy. And we do have the despacings and the intensities that you would need for your phase ID. But as you can see, there's significantly more information here. And now let's talk about what some of the capabilities are within the PDF entry. And one of the first things is that you can observe is that you can change the wavelength that you're working with. Now that will not change the despacing, won't change the intensity, but it will change the 2 theta value based on what radiation you're working with. Default is copper K alpha 1 radiation, but you might be working with iron. You might be working with synchrotron data, and you can input your own wavelength. And what will happen is when you look at the column of two thetas, when you look at the simulated pattern here, you will see a change in the two theta. And this just allows you to get better visualization of what your material looks like from a phase ID perspective. So the types of radiation sources in terms of data that you can work with using the database, certainly laboratory X-ray data. We work with synchrotron data. When we have atomic coordinates, you can work with constant wavelength neutron data, and we can work with time of flight neutron data. So again, another feature that's unique to the Powder Diffraction File databases. We also are able to work with electron diffraction data. You can simulate electron diffraction patterns when we have the atomic coordinates. So that helps you with multiple techniques when you want to do your characterization. In addition to the, what I'll refer to as just the diffraction data for phase ID, some of the other features include looking at 3D structures, the electron patterns I mentioned earlier, ring patterns, and different types of diffraction data. So we see that you can plot out the 3D structure when we have the atomic coordinates available for an entry. You can look at bond lengths, bond angles, and get some kind of bond distribution information. You can look at the selected area electron diffraction pattern simulations, backscattered Kikuchi pattern simulations, ring patterns that you might see in a 2D detector. Those you can generate independent of atomic coordinates being present. If they're not present, that's fine. You can still simulate the ring pattern. You will have the ability to make a simulated diffraction profile you can compare your data to, and we are adding many entries to the database where we actually are including the raw data as part of the diffraction pattern. Now, if that data indicate it's a highly crystalline pattern, it may not look very different than what you're seeing, or may not look different than the simulated pattern. But there are cases where the raw data gives you enhanced analysis capability, again, something unique to the powder diffraction file. An example would be clay materials. So here's a PDF entry with raw data, halloysite 10A clay. Here is an icon up here that's lit up, so that means it's active. And what you'll see here in the diffraction pattern region, the traditional stick figures that people would use for D's and I's for identification. But the red pattern here is in fact the raw diffraction data, and you'll see that there's a lot of disorder typical of many clay materials. And this order can be observed in the raw data, but would never be able to be simulated in just a DI list. So having this raw data is an enhancement in terms of being able to do characterization. Other examples beyond the halloysite clay and other clays such as smectites and micas, we have polymer patterns. Here is Naphion used in many fuel cell applications, and you can see that we have the low angle ionomer peaks as well as the higher angle inter and intramolecular bonding of the traditional polymer. Again, the DI stick figures would not allow you to see this full profile. We have nanomaterial data sets in the database so that you can see the effect of broadening when you have nanoparticles. And we have a number of polymers such as cellulose 1-beta. This is one of the most common excipients in pharmaceuticals. So instead of just trying to rely on DI sticks for your ID and for your profile fitting, we have the whole profile present for the material that gives you better results when you want to do, for example, quantitative analysis. Example, using something that would have a whole pattern presence in the database. This was a rock specimen from Australia, and we analyzed 3 regions where we had the white crystals, this dark region, and then we have this glassy looking region as part of this mineral sample. And when we do the diffraction pattern in blue is the simulated pattern or the raw data pattern from the database. Red is the raw data from the sample, and we get a good match for gypsum where we have these crystals. In the dark region, we have goethite and a little bit of quartz that's present. And in this glassy region, we have identified opal. We actually have opal patterns in the database, and you can see the overlap of the reference pattern and the raw data that helps us to characterize completely what's going on from a phase ID perspective. Now, in addition to the diffraction data, you have property sheets in some of these entries. And if the property sheet icon is highlighted, you can click on that icon. This is an example of graphite oxide. And we've added additional diffraction data to show the effect of humidity on the OOL diffraction peak because water intercalates between layers of the graphite oxide. So as the humidity increases, the basal plane spacing also increases. So you go to lower 2 theta, larger D spacing, and then as the humidity decreases, you'll see that that D-spacing or peak position changes. We tabulate that data here so that when you're looking at graphite oxide and your pattern doesn't match exactly to the singular PDF entry, we have this additional data that you can look at and say, yes, it's summertime, the humidity is up, I'm going to see a larger spacing than in the wintertime when the humidity is low. So again, a physical property, but something to help you get better characterization of materials. Now, sometimes the property sheet is not diffraction data, but some type of true physical property. Here is a perovskite material. It's a mixed rare earth cobalt oxide perovskite. When we look at the property sheet, in this case, it is a thermal expansion coefficient property sheet. So we have data for the mixed rare earth oxide as well as the singular rare earth oxides. And we can see the effect of temperature on thermal expansion. And this provides some information in terms of maybe there's a phase transition taking place, or how does this material behave, and what's the change in lattice constants as a function of temperature. Again, more information to help you with more complete characterization. We also have data that comes from a wide range of sources. And by being able to pull all of that data together in one location allows us to develop temperature series. So here is a corundum aluminum oxide entry. The temperature series icon is highlighted, and when you click on that, it will ask you, do you want to restrict it to just phases that have the same space group, in this case R3 bar C, or do you want to look at all aluminum oxides? So if I restrict it to just what is the effect of temperature on the corundum type aluminum oxide, I can click on restrict the space group, and I'll come up with a table of entries, and it shows a range of temperatures for this type of aluminum oxide that we can now do further analysis with in terms of materials characterization. You can plot out the simulated patterns of all of these entries based on the D-spacings and intensities provided with the data extracted into the database. And we go from low temperature to high temperature. The tick marks here start at low temperature and go to high temperature. And you can see how the diffraction peaks shift to lower angle, larger D-spacing as a function of temperature. You can now take this information and you can pull out additional, I'll call it materials characterization information. Here is an example, a plot of the cell volume versus temperature. And from that, we can get the cell volume thermal expansion coefficient. You could do this for the A lattice constant, for the C lattice constant, and get individual expansion coefficients. Another way of extracting more data from the database because we are pulling together all of the data from multiple references. So with that, we're going to do a database demonstration. All right, so now let's share, and we're going to now go to PDF4 Plus. When you open up PDF4, this is that initial search menu. And one of the first things that I like to do is change the font size a little bit just to make it a little easier to read. You can go up to the icon here called Preferences. Under Preferences, you can look at the General tab and change your font size. For our purposes today, I'll make it 175%, just so that it expands everything and a little bit easier to read. And certainly you could make this adjustment depending upon what you're comfortable with when you're working with the database. So here is our particular search menu. And as I mentioned in March, we'll be having a webinar that focuses on data mining. We will do one example towards the end of the webinar today, but our focus right now is to look at opening a PDF card. So if we come up to the upper left-hand corner where it says Open PDF Card, we can enter in a particular number. This would be a number. This is the case where you know the materials you're working with. So we're going to use as an example 00. So that's going to be coming from our ICDD data, set 65065, and then it's going to be entry or card number 0110. Now you'll notice that I have highlighted right now to recent PDF cards. So I have different PDF entries that I've been working with. But on top of that, you can also look at popular PDF cards. So if there's a particular set of entries that you're continuously working with, you can certainly have that highlighted so that you can easily call up things that you normally work with in your laboratory. So we'll go now to open up this PDF entry. And here is the entry or card. Both terms work here with what we're looking at today. And what do we have? Well, we have the traditional DI list. You can scroll down and see the various peaks, the intensities. This particular entry, the unit cell, must be known because we have the HKL Miller indices. You'll see a star here. If the material is a modulated structure, it will have the modulated indice as well, but this particular entry is not modulated. And you'll see in the column here, 2 thetas. 2 thetas now can easily be shown in a electronic-based PDF entry where you're not worried about having that card handwritten or printed despacing list. And we talked about you can change your wavelength that you're working with. I have set up right now for copper K alpha 1, and you'll see the pattern plotted here is the 2 theta versus intensity. If I go and say instead I'm working with iron radiation, and when I click on the iron K alpha 1, what will happen now is my 2 theta range change, the 2 thetas here change, but these spacings will stay the same because that's a function of the unit cell type. If you were working with synchrotron radiation, you can go to user defined. It could be any wavelength, but you can put in some wavelength that you're working with in terms of synchrotron or other radiation. Enter that information, and now we see again the 2 theta range has changed. So it gives you flexibility to work with any radiation that you're using in your laboratory. Now I'll go back for the moment and put the copper K alpha 1. But if you said, hey, Tom, I'm working with iron radiation all the time. Is there any way that I can make iron my default value? You would go up to the preferences icon again, click on that, go to diffraction pattern. And at this point, this is where you could enter in whatever radiation you're working with. That could be entered. And then when you apply that, it would be saved as your default radiation other times when you open up the database cards. So in addition to this flexibility here, there are a number of things that you would look at for a PDF entry. Initially, it opens up with the PDF tab. This is where you'll get your chemical information on the phase that you're looking at. Here's your quality mark for the entry. If it is known, any temperature or pressure information for the data collection, that will be included as well. On the experimental tab, it talks about how the data were actually collected. This is something we extract from the literature or provided through our grants program. If it is unknown, then the information will not be provided. Was collected with an internal standard on a diffractometer. This cutoff number is essentially used to tell you what was the starting range from a 2 theta point of view so that you know the maximum despacing that would have been observed with the data reported in the literature. So if there is a 20 angstrom peak, what will happen is you would not see it in the data set reported in the literature because it did not go to low enough 2 theta. You have physical information, if we know crystal system, space group, unit cell, volume, Z, etc. If there's any density information, and then the figure of merit, Smith-Snyder figure of merit based on the delta 2 theta and how many of the first 30 peaks were observed. We have crystal information. Sometimes there is a crystal cell and it can be reduced to a different cell. If that's the case, we would have that information. This particular material, the structure is reported, so we have the atomic coordinates. And this is important if you want to do things like felt refinement or hole pattern fitting. Depending upon the manufacturer software, all of them are compatible with the ICDD database. They extract the D-space, they extract the intensities for phase ID. Our Jade software also has the atomic coordinate data already available so that you can immediately do hole pattern fitting. But if you want to use a program that you need to extract this data, you can come up to export, which is in your PDF card, and you can convert it, for example, to a CIF file. So you would convert the particular PDF number, it would be a CIF file, and then from there you could extract that and use that in any Rietveld program. You have classifications, so it falls in our subfiles, inorganic, Pearson symbols presented, Wyckoff sequence. If prototype structures are known, that information will also be provided. You have a tab here called cross references, and this is just an indication that there are other entries in the database that are similar in structure and composition. Those entry numbers will be presented. You can double click on one of the cross reference entries and that PDF card will open up and you can look at that particular entry to see if there's any additional information. You have reference information, where the sample came from. Hey, T. Blanton, pretty good guy here. And then if there's any unit cell information, we include that as well so that you can look up the literature. More current entries and more current literature references now also include DOIs so that you can click on the DOI and at least see the abstract for that particular literature reference. And if your institution has a subscription, you can also get that literature manuscript. I will highly recommend that when you're looking at a PDF entry, review the comments because the comments often has a lot of information such as how the sample was obtained, how it was prepared, if there are any polymorph issues, are there any issues when you were looking at collecting the data. That information is here. It's very useful and I would highly recommend looking at that on any new entries or any new data that you're studying. So we have what I'll call sort of the experimental, the crystallographic information here. In this particular entry, you also have some of the features such as able to look at the 3D structure, and that's because we have the atomic coordinates. So if I click on that tab, you can see the 3D structure for this material. You can look at multiple unit cells here so that if you wanted to look at a 2 by 2 by 2 lattice and then you wanted to look at, for example, here, rotate the molecule around, and do you see here we have channels? This happens to be an ionic conductor material and allows you to visually see where the silver ion is able to channel through this particular structure. We mentioned that we have our bonding table, so we have bond lengths, we have bond angles, and you can look at that information to get some distribution function information related to this particular phase. We have the selected area electron diffraction pattern simulations, and you'll have a default 001 zone axis, but you can change the zone, so you can change the simulation. You have the ability to input your camera constant or your experimental conditions so that you can in fact change the view of the particular simulation. You can look at particular, we'll call it spots in the pattern here, your diffraction spots. You can change, do you want to be looking at despacings? Do you want to be looking in terms of reciprocal nanometers, or angstroms? Okay. You can change the color of spots. So there are a number of things that you can do in terms of looking at your simulated pattern. In addition, if you want to, you can import a pattern and overlay it with the simulated pattern to compare orientation and identification. We have the electron backscatter pattern simulation. Again, similar to the selected area electron diffraction, you can change your experimental conditions. You can change the particular zone axes that you're interested in looking at. You can move your cursor over any of the Kikuchi lines and see what lattice plane is being represented. You certainly have the option as well to change the color so you can make a particular image that you're looking for. So another capability when we have the atomic coordinates present in a sample. The ring pattern can be generated independent of having atomic coordinates. And you can change your sample distance. So we call it camera length, but this would be your sample to detector distance. You can make it smaller, you can make it larger. You can rotate the camera so that you can change. Maybe you're not looking with a symmetrical detector position. Maybe you're looking something where you have in fact moved the detector line. You can change your XY position with it there. So that you can say where a simulation of where my detector was located in a given sample. You can multiply intensities to make light lines or low intensity lines more intense. You also have the option to adjust simulated crystallite size, so that if you think you're looking at small crystallite size materials, you can see what the effect would be on broadening your simulation rings. As we saw with selected area electron diffraction, you can import a diffraction pattern, overlay it with your pattern to see how it compares, and you can put some degree of transparency on your pattern so that you can change the intensity of some of the diffraction rings. Now you have the ability to look at, in this case, the raw diffraction data. The icon is highlighted here. We have the checkbox here where that's what's plotted in red, but you can click on that icon and you can see what the actual raw data was for this data set that was used to develop that PDF entry. And if you wanted to, you could say import diffraction data. You could import your diffraction pattern, overlay it, and see how it compares. And we'll do an example of that with another PDF entry in a couple of minutes. You also have the ability to look at the simulated profile. And the simulated profile takes the DI list and puts a simulated diffraction pattern based on a defined profile, and the default is a pseudo void. So what you find here in the simulated pattern, there's an arrow here on the right. If we click on that, You'll see profile functions. Pseudo void is the default function, but you can also do Thomson, Cox-Hastings. You can do Gaussian, Lorentzian, and you also have an option to simulate crystallite size. If I click on crystallite size, it will actually simulate what happens to the diffraction pattern as I get to smaller crystallites or if I get to larger crystallites. Now, this is not a substitute for a whole pattern fitting technique, but it does allow you to get a quick simulation on what the crystallite size effect would be on my pattern. In addition, we have a preferred orientation simulation. This is a March-Delage function, and you can change whatever plane you're interested in, and you can look at what's the sample when it's random, what will it look like when it's more platey in nature, what will it look like when it's more needle-like in nature. So again, the idea is that if you overlay your data and you happen to see something that looks a little bit different in the peak intensities, you can do some preferred orientation simulations to help you characterize your material. All right, so that is sort of a general idea of what happens. We said we knew a particular PDF entry, but what happens if you don't know the particular entry number that you're interested in, but you know the phase? And this is now getting into something close to the data mining capability of the database. And I'm going to do one example for today. Suppose you're looking at cerium oxygen. So cerium oxide is what you're studying. And we have a Boolean search set up here that would be the AND function. So if I click on this plus sign, I'm now going to look for phases that have cerium and oxygen present. I would come down here to do a search. And when I click on search, I'll get 6,181 hits out of the 444,000 in the database. So let me just expand this a little bit here. And in the table of hits, I get the PDF number, I get the quality mark, and notice that, I did a search for cerium and oxygen. How come I have all of these other elements present? And the reason is that in the Boolean search, when you said cerium and oxygen, it also did not remove any other element. It just said you must have cerium and oxygen present. So they're there in all of these entries, but other elements could be there as well. So I'm going to close my hit result, and I'm actually going to reset this tab, and I'm going to change my search to only cerium oxygen. So now it will only find phases with cerium and oxygen, no other elements. Now, a couple things to pay attention to here. Once I activated a search in the elemental table, this tab here amongst all the search capabilities in our data mining became red, which helps to tell you it's an active search. Also, down here in the bottom right hand, you'll get a list of what's being searched on. So I have the elements, and you'll see something called status primary alternate. Status relates to what entries are being called up, the primary entries of a phase, alternate entries. We also have deleted entries in the database. Why? At some point, someone may have referenced a particular entry that was later removed because better data were found, or we found a problem with that entry. But you can certainly search on deleted patterns if you want to. We just don't do that as a matter of default. I'm going to go do my search again. And now I'm down to 217 entries. And you'll notice that now all of the entries here are some form of cerium oxide. And later in the March webinar, we'll learn how you can even be more selective to say, I only want a particular composition. But let's look at the hit list here. The default is an order of PDF number, starting with set 00, 01, then 0304. Quality mark are listed here. One of the things, if you wanted to say, show me just the, or let's put in order the high quality marks, click on the QM, the heading of this particular column, and what it will do is it will align all of the high quality marks, then the mid quality marks, and then finally the lower quality mark issues in order. If you click on that particular column tab again, then you will get the reverse order or hypotheticals, then the lower quality marks, and it will go up to high quality marks. At any time, click on PDF number and it will put it back in the original order. You can search on compound name. All of these are some kind of cerium oxide. You can also do sort of a quick Hanawalt type search where you can order it based on despacings, low to high or high to low. You can do it for the second most intense peak, third most intense peak, if you just want to get a quick idea where, for example, a certain despacing is showing up. You'll also see this SYS. This is the crystal system, where you could click on that and it'll put A for anorthic, the triclinic lowest symmetry, then monoclinic, orthorhombic, tetragonal, hexagonal, rhombohedral, cubic. You can do the reverse and it'll put the cubic up top. If you wanted to, you can add additional fields. You would simply go to the fields and select what you wanted to see. So for example, if I went to crystallography and I wanted to see the space group, that would then also be displayed here as well. And anytime you wanted to remove a field, right click on it and just say remove. All right. So I'm looking at my particular entries and I'm going to open up this one here, 0034394. So the idea here is that when you do not know your PDF entry number, that's what the data mining will do for you. So I'll open up this particular entry. And as I look at it, I see that it is a phase of cerium oxide. And one of the things that I'll look at quickly is where did this data come from? So I click on references, and it was collected at the National Bureau of Standards. Today it's NIST, NIST, but previously it was MBS. I can look at the comments. The comments will tell me something about how the sample happened to be made. Structure, I see some atomic coordinates here. But what I want to do is now say, I think I made some cerium oxide. Can I compare it? Well, we don't have any raw data here, but we do have the simulated pattern. So let's click on that. Here is the simulated pattern based on this PDF entry, and I want to import my raw data. So I would go up to plots, import a diffraction pattern, and the particular pattern I'm interested in, I can say open, and this is the raw data. Now I can do some analysis with this data. I could find peak positions, I could remove background, or I can simply import to overlay. So we'll see the simulated pattern here in red. You see the tick marks showing where peaks are located based on the PDF entry. If you put your cursor on any one of these, it will tell you the 2 theta angle based on copper K alpha radiation, the D space, and the HKL if that's known for the particular phase. Well, you'll see that I only have a limited range in my raw data up to 70 degrees 2 theta. So I'll simply take my cursor, drag it across here, and just focus on the raw data versus the simulated pattern. And I would look at that and I would say, yeah, I've made cerium oxide. It's a good match. However, my profile for my simulated pattern doesn't agree as well with my raw data. And the reason is that my sample that I made that generated the raw data is a nanomaterial. So I'll go over to my arrow on the right, look at my profile function, and let's do a simulated crystallite size to see if we can get a nominal size for my material that I've made. Crystallite size, and we see that the default of 25 angstroms, the peak is too broad, so that's too small of a crystallite size. So I have options here that I can use my slide bar to change the crystallite size. I can input a number here, or I can use my up-down arrows to increment what we have here. So I'm going to put in a crystallite size, and as I make my adjustments, as I make it smaller, I see my simulated pattern increasing in breadth. So I'm somewhere around 85 angstroms. Now my tails don't agree exactly, and there you can play with the crystal variance, which is sort of a distribution of crystallite size. And I could increase that a little bit and get something that looks close. And you could adjust these numbers back and forth a little bit till you get something that you say, this is pretty close. Now, as I mentioned earlier, this is not a substitute for whole pattern fitting, but it does let you get a very quick idea about the nominal size of the material you've generated based on the PDF entry. So this is just a quick example of doing data mining, a very simple example of doing a periodic table search. And later in our webinar series, we'll go through the more details on how to use all of the features for data mining. So I'm going to close now the live demonstration, and I'm going to go back to the presentation here. Okay. All right. So we did the database demonstration, and what are some of the things that to summarize what we did today? We talked about the PDF databases. Today's emphasis was on PDF4 Plus. We showed you how to open a PDF entry when you know the particular entry number. Once you have a PDF entry open, whether you call it an entry or a card, we talked about the features and tools in the entry. So your diffractometer software typically is going to extract the despacings, intensities, and chemistry information, but the PDF entry has many more tools, and we've talked about how to use those tools. We then finished with a short demonstration of an example of a data mining search that when you did not know the PDF entry number, you can do an elemental search in the PDF4 database to help you find entries that might be of interest for your material study. Just a point of interest that if you want to reference the powder diffraction file, there's a paper written in 2019. It was in the Powder Diffraction Journal. It is available for people to look at. This is the reference here, and you can find access in terms of the reference on our website that I'll mention in a moment. But if you have a question or would like to get a hold of this reference, please contact us and we'll help you get that information. So this is the near conclusion of our first webinar, InSession webinar. In February, we'll be having a webinar talking about navigating Jade. We have our March, April, May, June webinars set up, and the next webinar will be February 24th. So you'll be getting a notice about that. So save the date. We'll talk about another application for materials analysis, but consider also that we have the additional webinars that will get into some of the more advanced capabilities of both PDF4 Plus and Jade Pro. So on behalf of everyone at ICDD, we'd like to thank you for attending. And we hope that with this webinar, you gained some insight into the capabilities of the PDF4 database and how it can help you in your materials characterization.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on ICDD.com. Contact us at info@icdd.com.